G'day all, I'm Greg. We're talking about text in games applications. I think text is as relevant today or more relevant than ever. We need to display lots of information to users. We need to collect information back from them. And you've probably been typing into your phones and things to realise that. The challenges in the last few years have been high quality internationalisation and probably high DPI screens, very small screens, very high resolutions, put a bit more expectation on us. This is where we sort of started a long time ago. You'll see the ASCII table there in a bitmap. Bitmap's nothing more than just a 2D array of zeros and ones representing lit and unlit pixels. And the ASCII table is quite adequate if you're English, European, or like card games, I guess. The next step we get to, and you probably all use tools like this, you've maybe got your application running a game or something you're starting up, you've got some triangles on the screen with your DirectX, your OpenGL, and you want to put some text on the screen. And then you go, how do I do that? Where's the OpenGL function for that? And it doesn't exist. So you Google and you find tools like this, or you write one. You're going to have to rasterize the true type into bitmaps and probably pack them together into texture, called texture pages. And that seems like you've got something going and it's working. But what about if you'd like to use a lot of different fonts? What if you have text chat in a game and people start typing characters that you didn't put in your atlas? What if you want to use different size characters, vastly different sizes? Maybe you can store large characters and shrink them down. Maybe not. So the next thing you might try doing is runtime caching. And this is what you're going to use. You can use FreeType because it's open source and it's free and it's very good. So you're going to rasterize the TrueType fonts into bitmaps at runtime, cache them into texture pages, pretty much what that tool did, but you're doing it at runtime instead, which gives you great flexibility. You're going to store, you're going to try and collect or use the system fonts rather than package canned textures with your game. And you end up with something like this in memory. You're going to be adding to this, maybe a bit more space between characters. So it'd be nice if things were this simple. Have a bitmap, have some offsets and stick a character on the screen and space across. But unfortunately we can't. To have a quick look at UTF. We started with ASCII. There's been many different encodings, but UTF's what we're using here on out. And they come in a bunch of different sizes or flavours. So it seemed like a really good idea. If one character, 1 byte was enough for English, then surely 2 bytes was enough for everything else. There's a lot of problems with that. It seemed like a good idea, except that there's more than 65,000 characters possible. Not good if you like scientific symbols or ancient languages, perhaps. And although it did seem simple to step across 2 bytes at a time, you can't guarantee that because surrogates mean that you actually have sometimes 4 bytes for a single character.
Well, there's a difference between UTF-16 and UCS2. So UTF-16 can do multiple.
Yeah, look, you can get away with it a lot of the time. UTF-16 looks a bit like this, and for most of the characters, you've just got 16 bits of a raw code point or a raw number, which is all you need. But sometimes, if the top bit says otherwise, there's more to come, and you may need to use 2 bytes. But you're not going to be able to use your old string library or things that you may have had around. Pretty much everything these days on the web is UTF-8. It's sort of a encoding that makes sense. It's backward compatible with 7-bit ANSI. It's certainly efficient for the English Latin type alphabets. You can look at a bunch of random bytes and you can find where the characters start and end quite easily, so the encoding's straightforward, don't have to worry about Indian. The biggest problem is that a single character is between 1 and 4 bytes. The original spec was up to 6, but 4 bytes is good enough for everyone. More code space. Whoops. Now we get to UTF-32. UTF-32 isn't really encoding because there is no encoding or decoding step. It's just a full number. Very handy, uses lots of memory, but when was the last time you ran out of RAM from storing text? In fact, you used to get those stats, hey, this piece of memory, this disk can hold how many copies of the Encyclopedia Britannica? I'm not sure how many people ever stored the Encyclopedia Britannica. Anyway, that's the current limit, but there's no reason we couldn't get past that limit if need be. And what you do is internally, you might store on disk in UTF-8 when you're working with it for rendering, for in edit boxes and things, work with it in UTF-32. Just skips the encoding, decoding stage. No processing, and memory is cheap. So you've got your text on the screen now, and you fill the screen with text and your frame rate drops, and you go, oh my goodness, what happened? Well, it turns out that you can draw 500 things on screen. You can either draw 500 triangles, or you can draw 500 batches of triangles, where each batch is perhaps a few hundred or a few thousand triangles. So the way to get around it is to batch, and this is really true for DirectX 9, 11, and even OpenGL, but to a slightly lesser extent. It's more of a driver thing. You get around it by grouping your textures, using as few large texture pages as possible. If there's anything varying, like maybe colour per character, stick it in the vertices so that you can draw lots and lots of triangles on the screen in one go. And you'll find you can draw most of your text in just a few draw calls. That's what you're trying to reduce, the number of draw calls. Don't draw one character at a time. So then when the user goes to input some text, you suddenly have to write something or figure out what to do. On the bottom left there we see an IME, an input method editor. If you work in Asian fonts, you'd be very familiar with that. You have to build up characters, partial glyphs at a time to make a full character, or a full word as it might be. Writing your own is a pain. Working with Windows can also be a nuisance. And after you've written one English keyboard, you realise there's actually lots of other languages in the world. It's best to just use the operating system. If you're a Windows program with DirectX 11, you can use full screen apps. You can use a flip swap chain, and then the Windows pop-ups will work with your swap chain. So you'll get the correct ordering. You can pop up a on-screen keyboard on top of your full screen native app. Okay, you couldn't easily do that before. It's very handy. So now you've got your text on the screen, and then suddenly someone decides to type in Arabic or Hebrew, and that's right to left. We're into another problem. The problem is that although they display the text right to left, it's actually stored left to right. So we have a logical and a visual mapping. And it's not actually clear or simple to where your text should change directions. More so, quite confusing, you see from that picture there, when you go to select some text which has got mixed direction, it's very common to have English at least mixed with other languages, what's the selection going to look like as you cross boundaries between different directions? Well, it looks like that. You end up with gaps between it. That's if we select logically and display visually. You've got multiple selection blocks. You could also select visually, but it's even more complex to try and write that. Luckily, open source to the rescue, we have FreeBIDI and MIDI-BIDI. So different licenses to be aware of there, but otherwise, FreeBIDI and MIDI-BIDI both take in your logical text and hand you back visual text with an array of mapping, so you can go backwards and forwards between the two, which you do care about if you want to make an edit box, because you would like to know what you're clicking on. So people who have started with text will often say, oh, does your font system do kerning? Kerning means that characters can overlap visually for a nice effect, swirls, and particularly proportional characters are going to be spaced up closely to each other. Certainly makes the text look better, but that's not that's the easy bit. That's implemented within the TrueType fonts as a kerning table, just a bunch of character pairs. Now we get to the interesting stuff. It turns out that one character can actually be multiple glyphs, or one glyph can be multiple characters. Sorry, that's the other way around. One character can become multiple glyphs. Multiple characters can become one glyph, sorry. So these here, we've got some Fs. You type two Fs together, two characters actually form, they bunch together and become one. But then other times, I don't actually have any good examples here. Some of the ones with ligatures or little accents, you type one character, but it actually has the accent as a separate glyph to the main character. So we have a many and many, one to many in both directions. So how do we resolve this? Unfortunately, it's tables, lots of tables and conditions. Thankfully, someone else wrote it for you. So we have HalfBuzz, another open source library with, I believe, a good license. And that is a text shaping engine. So shaping is going to take your text, you've already converted it. It actually does a whole bunch of stuff, but you can pass it your visual mapping, and it will give you back a code point to glyph table. So now you can display, and offsets as well. It does everything for you, really. You can pass in some UTF-32 and get something like that Arabic text off the bottom there, where those little accents and dashes above and below are actually multiple glyphs overlapping each other. Okay, so you're going to want to do some word wrapping. Word wrapping sounds straightforward. You're going to keep putting, split your text into words. When you run out of a line space, split the word or put on the next line. But where is a line in different languages? So you're going to need a rule set to split that. I'm not really sure where you get this from. I found some open source code from Microsoft that does word wrapping in a number of languages. It seems to work just good. High resolution screens, right, we have to speed this up. So all sorts of screen size and shapes. We want to draw text with anti-alias quality at different resolutions. So a good modern way to draw that is to use sign distance fields. Forget the sign so much. The important thing is instead of storing just a alpha transparency like that there, we store a distance field. And what we're doing is we're encoding, just use the alpha channel of your texture, same thing. How far are we from the edge of the character? What is inside? What is outside? Where is the edge? And because it is a field and we're using the texture sampler, literally that sampler inside the GPU, we can find precisely where that line is. The end result, you can see smooth scaled text. But since we have a distance, we can do more. We can do anti-aliasing, outlines, shadows, scale up and down, and since we're decoding in the shader, we can offset for some LCD subpixel sampling if we want. So sounds all good. What is the catch? Not very many, certainly worth doing anyway. You can lose sharp corners, but you can correct that by storing 2 distances instead of 1 if you really care. Actually creating a high quality table that looks like that bottom right picture there is a bit of a challenge to that. You can certainly get some open source code that'll take an alpha map and just convert it, but it really depends on how the edges were shaped to what quality you'll get. Okay, what's the future? Ideally, we'd like to rasterize in shader directly from the TrueType splines. Okay, there's some projects doing that. Microsoft has a project, excellent project by Gliffy, the guy who's main contributor to HalfBuzz and FreeBDE, has also wrote Gliffy, which does exactly that. Converts the splines into an intermediate format and then renders them in shader, just like that. It is a little slow though. There are some limitations, but certainly keep an eye on. Automated layout, if you're working different sizes and shaped screens, you're going to have to lay out your text. You don't want to hard code, as projects I've seen before, umpteen resolutions, where things lay out on the screen. Use your stack panels and grids along with your scaled fonts to try and keep that touch size or that visual size. Since we're working in 3D, and remember text in 2D is really nothing more than 3D with a orthographic projection. Transform your vertices, you've got full 3D effects. Just remember that if you want to do a projection effect like that up in the corner there, you've got to store the W. Okay, the W occurs, recall, after the vertex shader, so you've got to pass a full four components to that shader. Okay, so putting together the text layout process, we've got to unify the direction of the text, itemize it into words or boundaries that are of the same direction, wrap the text, and while we're wrapping, we're going to measure and convert into glyphs using a shaping tool. Okay, so summarize, we want the high DPI, high quality fonts, anti-alias quality, we want a full set of international fonts, we want to display accurately, basically handle all that can be thrown at us, and we're going to use the built-in on-screen keyboards and method editor, distance field rendering, runtime caching from TrueType, UTF-8 on the disk, UTF-32 in the process, text layout and so on with HalfBuzz, FreeBDE. Thank you. I think we're out of time for questions.